Chapter 29, Induction and Inductance. Induction and Inductance covers Faraday's law of induction, Lenz's law, induced electric fields, inductors and inductance, self-induction, RL circuits, mutual induction, samples. You can find them in the timeline. Faraday's law of induction. Two systematic situations. If we put a closed conducting loop in a magnetic field and then send a current through the loop, forces due to the magnetic field create a torque to turn the loop. Current loop plus magnetic field, which produced a torque. We have a reverse question. If in the magnetic field we apply a torque to the loop, will it produce current? The answer is yes. That's Faraday's law of induction. It's from United Kingdom. Two experiments. First experiment. We have a loop on the left, connect with a meter. And then we hold a magnetic field put into the loop.
These wire coils and this bar magnet will be used to show electromagnetic induction. The three coils are wired in series to this galvanometer so that current in any one coil will deflect the meter. Here is a single bar magnet pushed slowly into a 10-turn coil, south end first. Here is the same action with a faster push. Here is the magnet being pushed into a 20-turn coil. Here is the magnet moving into the 40-turn coil. Here's the magnet turned around, moving north end first, into the 40-turn coil.
One, a current appears only if there is relative motion between the loop and the magnet. One must move relative to the other. The current disappears when the relative motion between them ceases. Two, faster motion produces a greater current. 3. If moving the magnetic north pole towards the loop causes, say, clockwise current, then moving the north pole away causes counterclockwise current. And moving the south pole to or away from the loop also causes current, but in the reversed direction. The current produced in the loop is called an induced current. The work done per unit charge in producing that current in moving the conducting electron constituting the current is called the induced electromotive force. And the process of producing the current and electromotive force is called induction. Second experiment. We have two loops. On the left is the same as the first one. Two loops are both addressed, and this loop is connected to an electrical circuit with resistance and battery.
We'll use this wire and a large horseshoe magnet to demonstrate generation of currents from motion in a magnetic field. The wire is hooked to this galvanometer to measure the currents produced. When the wire is moved in the field of the magnet, the meter deflects. As soon as the motion stops, the meter goes back to zero, showing that the current has disappeared. Pulling the wire back out of the magnetic field produces a current in the opposite direction. If we turn the magnet over and repeat the same motions, the directions of the currents are reversed.
Switch on the right lobe, the meter suddenly and briefly registers a current, an induced current in the left lobe. Switch off the current in the right lobe, and another sudden and a brief induced current appears, but in the opposite direction. 3. An induced current appears only when the current in the right lobe is changing.
These two coils are not connected electrically, but we can use a current in one to induce a current in the other. When this switch is pressed, a current flows in the first coil as seen on this ammeter. Any current flowing in the second coil will be shown on this galvanometer. When the switch is pressed and released rapidly, a current is seen in the second coil. If the switch is now pressed and held down, the current in the second coil pulses rapidly, then drops to zero, even though current is still flowing in the first coil. If the switch is released, what will happen to the current in the second coil? The current pulses rapidly in the opposite direction. If we remove the iron core running between the two coils and repeat the demonstration, the current in the second coil drops dramatically.
Faraday's law of induction. Faraday realized that an electromotive force and a current can be induced in a loop, as in our two experiments, by changing the amount of magnetic field passing through the loop. He further realized that the amount of magnetic field can be visualized in terms of the magnetic field lines passing through the loop. Faraday's law of induction, stated in terms of our experiment, is an electromotive force is induced in the left-hand loop in Figure 1 and 2 when the numbers of magnetic field lines that are passing through the loop is changing. Most important, the actual number of the field lines passing through the loop does not matter. The values of induced electromotive force and induced current are determined by the rate at which that number changes. A quantitative treatment. We define the number of magnetic field lines that they pass through the surface's area by the magnetic flux phi b. We define phi b equal integration b dot dA. We know the integration actually is a sigma, right? Yeah. So we dot this one equal, where dA is a vector of magnitude dA, that is perpendicular to a differential area dA. You have two directions for a perpendicular dA that you can define by yourself. And the integration is to be carried out over the entire surface. This integration. The metric system unit for magnetic flux is Tesla square meter, which is called the Weber, abbreviated WB. 1 Weber to 1 Tesla square meter. Here are the general means by which we can change the magnitude flux through a coil, because it's defined phi b equals integration b dot dA. B dot dA is b dA cosine theta. Theta is the angle between b and dA. So first look at a b. Changing the magnitude b of the magnetic field within the coil. Then the blue one, dA. Change the area of the coil or the portion of that area that happens to lie within the magnetic field. For example, by expanding the coil or sliding it out of the field. 3. Change the angle between the direction of the magnetic field B and the area of coil. For example, by rotating the coil so that E is first perpendicular to the plane of the coil and then is along the plane. Faraday's law of induction. Epsilon equals minus d phi dP. This is induced electromotive force. This is the change of magnetic field. So this means change magnetic field can change electric field. The magnitude of electromotive force induced in a conducting loop is equal to the rate at which the magnetic field flux FB, so that lobe changes with time. For a closed packed coil of n turns, we just mentioned one turn, now you have n turns. We just multiply n in front of this. This is a volt, Weber per second.
This wire coil can generate an electric current using the Earth's magnetic field. Turning the coil in this direction generates a small current, which we can see on a galvanometer. If we move the coil sideways without rotating it, no current is produced. The magnetic flux through the coil changes as the coil is rotated, producing a current. The flux stays constant as the coil is moved to the side and no current is produced.
These two coils of wire are suspended from pendulum arms. The coils are electrically connected through these steel rails, so that any current flowing in one coil must also flow through the other. When one of the coils is swung in the magnetic field of a large horseshoe magnet, the other coil also begins to swing between the arms of its own magnet. If one of the magnets is turned around, the second coil swings in the opposite direction as the first coil. If a thick wire is connected between the steel rails, shorting out the current, the effect stops. When a wire coil swings between the poles of a magnet, a voltage is generated in the coil. We'll use this coil connected to a small light bulb to show how that voltage changes as the speed of the moving coil is increased. If we swing the coil into the magnet slowly, the light bulb does not react. A slightly faster swing produces only a dim light. A faster swing lights the bulb brightly. This wire coil surrounds a long iron core. We'll run an alternating current through the coil and watch the effect on metal rings placed over the iron core. This copper ring rises up above the coil and floats at a constant height. A lighter aluminum ring flies completely off the core. If we use this aluminum ring with a small gap, it doesn't move at all. If we cool the solid aluminum ring in liquid nitrogen and repeat the demonstration, It flies even higher than before.
Sample. The long solenoid as shown in cross-section in the figure is 200 turns per centimeter and carries a current I 1.5 ampere. Its diameter D is 3.2 centimeter. At its center, we place a 130 turn closed packed coil C of diameter D 2.1 centimeter. The current in the solenoid is reduced to zero at a standing rate of 25 milliseconds. What is the magnitude of electromotive force that is produced in coil C while the current in the solenoid is changing? Now, the current in the solenoid changing is in 25 milliseconds. It changes from maximum to zero. My question, in 25 milliseconds, we have induced electromotive force. Then this end is the turn of this coin where we want to find it. Okay, so now this is the B in the magnitude field produced by the solenoid. Is mu 0 I 0 n. We learned before. This is the area of the small coil called pi r squared or pi d squared over 4. We'll put number inside. This is a constant. This is 1.5. Now this is n. N is defined by turns per unit length. Here the length should be meter, and the given data is per centimeter. So we have to multiply by 100 because 1 meter equal to 100 centimeter. Then we get answer. N is delta phi of delta t. Delta t is 25 milliseconds. Delta phi is from top to zero. This one. 75 millivolt. Lenz law. Uninduced current has a direction so that the magnetic field due to the current opposes the change in the magnetic field that induces the current. Suppose we put the magnet into the pole. This is north. Okay? So we will find the induced current will produce magnetic field too. It was always against the change. So this is north to north. You have to repair force, reduce it. Okay. So in this case, the current in this way. This current produces magnetic field. This is north. This is north. So you need force this magnetic field into this way. You do the work. You have to do work, and this work has been transferred to the thermal energy of this loop. Okay. Energy consumed. Let me repeat it. Uninduced current has a direction such that the magnitude field due to the current is the current, this north, opposes the change in the magnetic field that induces the current. So this is end-to-end opposite, repair it. This induced magnetic field does not intrinsically oppose the magnetic field. It opposes the change in the magnetic field. That's different. Now, we look this one. Okay. If the magnetic field increases the direction, so it will induce current, which opposes the change. In other words, the induced current should opposite direction. Okay. So this is current opposed to change. Now, if the same B, it decreases, change it. So we go to oppose it. What happened? So the induced one will induce a magnetic in this direction. Now, look at this. If the magnetic field increases direction, so the induced current will oppose it, will go to opposite. So this is the direction. If the magnetic field decrease, so the induced current will oppose decrease, so it will approach a B this way. So it's the direction. Okay. Electric guitars. We saw a lot of electric guitar in galas, in concerts. Okay. This is a metal guitar string. This is coil magnetic field. The oscillations of metal strings are sensed by the electric pickup that is send the signal to a magnifier and a set of speak. As the string oscillates towards and away from the coil, the induced current changes direction at the same frequency as the string's oscillations. Thus, relays the frequency of oscillation to the amplifiers and the speaker. Example. Fixtures a conducting loop containing a half circle of radius r 0.20 meter and the three straight sections 1, 2, 3 straight. The half circle lies in a uniform magnetic field of B that is direct out of the page, direct to you. We see all the head of the arrow. Okay. The field magnitude is given by B equals 4.0 t squared plus 2.0 t. Its timing changes, it's not constant. It changes with time, but not with location. Okay. With B in Teslas and T in seconds. An ideal battery with electromotive force 2.0 volt is connected to the loop. The resistance of the whole loop is 2.0 ohm. Question A. What are the magnitude and the direction of the electromotive force induced around the loop by field B at t equals 10 seconds? B is a change with time t, so this is we give you the time at this moment what is induced electromotive force. By definition, epsilon equal to minus d phi b dt. Here, d phi b dt only this part. This is no magnetic field. So B dot dA. If B, we choose to A. B is parallel to A, and in the same direction. B is this direction, the A is direction. So we change the counterclockwise is a positive number, A. Okay? It's towards you. So B dot dA equal to BA. BA. This we from this to this, we means B parallel to A, and B is in the same direction as A. So A is this direction. So B is direction. A is direction. So this is loop's direction is counterclockwise. Is when we do this one, we assume this is a current, positive current direction, counterclockwise. So we put this one inside. A is a constant, so dB dt. Then we get epsilon equal to minus d phi dt. Okay. Then epsilon equal to minus A is this one, half pi r squared. dB dt. B is 4.0 t squared plus 2.0 t plus 3.0 dt. And this one, we do the derivative, is 8.0 t. This one, 2.0. This one, 0. So we get epsilon equal to 8.0 t plus 2. And this t is 10 seconds. We put the t in 10 seconds, we get epsilon. You see this one number, this is minus number. What does this mean? This is clockwise. Epsilon, this one, and this is clockwise. Why? You see, d phi dt is a positive number. That means it goes more and more. And so the induced current must against it. So you produce flux. B is this one. So the current direction must be clockwise. You can produce E against the change. Question B. What is the current in the loops at 10 seconds? This is I epsilon net over I. Remember, we have connected actual electromotive force, and this is direct direction, and our direction is clockwise. So we look at the clockwise. This is E induced minus E battery. This direction is this direction, clockwise. Induced electric fields. Induced and energy transfers. We have learned the induced electric magnetic field and current. Okay. By Lenz's law, whether you move the magnetic field towards or away from the loops in the figure, a force resists the motion, requiring you apply force to do the positive work. This source, you have to push it in, you have to do work. At the same time, thermal energy is produced in the material of the loop because of the material's electrical resistance to the current that is induced. The energy you transfer to the closed loop plus magnetic system via your applied force ends up in this thermal energy. For now, we neglect energy that is radiated away.
This coil of wire is connected at the ends so that it forms one continuous loop. It hangs freely from a string so that it can swing under the influence of small forces. When one end of a horseshoe magnet is thrust into the coil moves in the same direction as the magnet. What will happen when we pull the magnet out of the coil? The coil again moves in the same direction as the magnet.
Pulling a closed conducting loop out of a magnetic field at constant speed. We look at this case. The magnetic field is limited in a square inside the space, inside the page. Okay. And we have a loop, we pull it out of this. So the area of this is getting smaller and smaller because we pull out. Okay. Since you pull it out, so the flux through this area is getting smaller and smaller, right? Yeah. And so anyway, it has induced current inside this loop. Okay. You have a current loop is in the magnetic field, so will be exert a magnetic field. F equal to I L cross B. Okay. In this case, by Lenz's law, the direction of current in this loop is clockwise. Okay, because when you pull out, there's less flux, so we have to increase it, and then we end up the induced current is clockwise. Okay, since you have a current, so each line of the loop will exert a force, IL cross B. We look at this by symmetry reason. They are the same in direction and opposite direction. Why? This point current goes this point current go this, so they cancel out. Only F1 is we have to deal with. Come on. F1 equal to IA cross B. I is here, okay, B inside, so F1 is to the left. Okay, to the left. Okay. So in order to keep the loop leading to the right at constant speed, we have to pull a force, which is opposite direction of F1 and the same magnitude. This is the one they have to apply this one. Okay? Yeah. You see this loop? Okay. Okay. This loop have a resistance R given. We have induced electric force, so you can find the I. This I equal to epsilon over R. In our case, it's d phi by dt electric field of R. And what is d phi dB? Phi. This is flux storage loop is air times this. This we assume x. X is the section of this loop inside the field. Okay, so it would be air x, this area BA. Okay, it's a flux. Okay, we know only x changes with time t. So this equal to B air over R is dx dt. And dx dt, the change of this length, actually is the speed v, right? Yeah, okay. So the induced current I is equal to B air V R. V is the speed, we put it up. Now, where is what we put I inside this one? We put I, there's an I, inside this B, and we got a B. Okay, we got a B. B air V over R air V, you get B square R square V over R. This is the force I have to use to keep it leaving the magnetic field at constant speed V. What is the power in this instant? The power mechanics is F dot V, is FV. They are the same direction. They are the opposite direction, but this one, the F dot B, okay, we F is this direction, it's this direction. So you could do this multiplied by B, we get a B square L square V square over R. This is the power, mechanical power I apply. Now let's see what the heat produced this one. You know, the heat produced one equal to I square R. What is I? I, this one. We put R, I square. This is this square over R. We get the same answer, B square L square, P square. So we see P mechanical equal to P thermal. Okay. The electric produced heat is supplied by me, mechanic. This is energy conservation. Eddy current. When we pull a metal called conducting stuff out of the magnetic field, we can assume they have some artificial loop, current loop produced because the same situation as we discussed before. This is clockwise. Okay. And this current is outside the B. This current is inside the B. So this current in B, you will be exert a force this direction. And me, I have to use force, pull it out. Okay, pull it out. And you have a current in metal, it will produce heat. Okay, heat. So when the metal falling down, so the magnetic field, it will be resistant to change. We want to pull it out, you want to pull it back. You change it, we will see that way, retarded. Okay, and heat produced. This is an induction stuff, not available in the market. Okay. To cook food on the induced stuff, oscillating current is sent through a conducting coil that lies just below the cooking surface. The magnetic field produced by that current oscillates and induces an oscillating current in the conducting cooking pan. Because the pan has some resistance to the current, so the electric energy of the current is continuously transferred to the thermal energy, resulting in a temperature increases of the pan and the food in it. The cooking surface itself might never get hot. Induced electric field. Let's see the situation. The situation is a copper ring. It's a copper ring. A radius R in a uniform magnetic field B external. It's uniform. In this case, into the page. To B external for fillets a cylindrical volume of radius R. Now this is a big R. If filling this one. No magnetic field outside, only within this area. B external increase at a standing rate. B increase. What happened? The flux, so this loop is increased. So the flux increase, we know it will induce electromotive force and induced current. The result, an induced electromotive force, and thus an induced current will appear in the ring. Okay, ring. A changing magnetic field produces an electric field. Okay, that's it. Okay. We see this current. This means you have electric field inside. From Ohm's law, how come you have a current? Because you have electric field, right, in a charge. Okay. So we suppose even without this ring, we cannot see any current, but the E still exists, right? The striking feature of this statement is that the electric field is induced even if there's no copper ring. This E direction. Okay, we need a direction. When B increase, okay, we induced E direction. Of course, vice versa. If B decrease in this direction, then E will change direction. A changing magnetic field produces an electric field even at places outside the range of B external. As long as the magnetic field is increasing with time, the electric field represented by the circle line in the figure will be presented. I will prove it. If the magnetic field line remains constant with time, there will be no induced electric field, and thus no electric field line. If the magnetic field line is decreasing with time at a constant rate, the electric field line will still be concentric circles at the figure. They will now have the opposite direction. This direction, okay? B is limited in a cylindrical volume in our case, but E does not. It can be everywhere. This is induced E. Now we look at 4 area. 1, 2, 3, 4. When B changes, the Faraday's law can be applied to any closed path that can be drawn in a changing magnetic field. We have 4. 1, 2, 3, 4. They're exact the same area, same shape. We can find when B changes, the electromotive force in 1 and 2 are the same because the area are the same. And electromotive force induced C is smaller because the area flux is smaller. Okay? And electromotive force in loop 4 is 0 because no magnetic field flux changes. And notice that electromotive force equal to 0 does not mean E along this one is 0. We will notice that one. There's different thing. A reformulation of Faraday's law. This one. Okay. Change magnetic field, produce electric field. Well, look at this. In the figure, the work done on a test charge Q0 in 1 revolution is, we around this one, we'll put the Q0 around one. So the work done by the magnetic field induced is epsilon Q0. This by definition, okay? This, and this epsilon equals this one. And also, if we look at it from mechanical point of view, this equal to F dot ds integration, okay? F for the charge Q is QE. S is along the tangent. In this our case, E is along the tangent. So they are parallel. We don't have cosine theta. Cosine 0 equal to 1. So, and then this is constant. E is constant by symmetry reason. So you can take out of this one. Finally, we get Q0 integration ds. Integration ds equal to circumference of the ring, 2 pi r. This is the work done by the electric force from different point of view. Look at that. They should be equal. And we make them equal, okay, and we get Q0 cancel out. We get epsilon 0. Epsilon equal to E 2 pi I. And we write this equation as epsilon equal to integration E dot ds. Of course, this extends the concept to this one. Okay. So electromotive force epsilon equal to E dot ds integration around the loop. Okay. That's the new. With this new concept, we put it in this direction. Epsilon equal to minus d phi dt is original Faraday's law. We just know epsilon equal to E dot ds integration, a new concept. Okay. So we put this inside, we get Faraday's law of induction. Epsilon E dot ds integration equal to minus d phi dt. This equation says simply that a change in magnetic field induces electric field. Now, phi b, we know is defined by b dot dA. There's no circle. Depends on the area. Okay? And we put this phi, we get a more fancy equation. It looks scary. Actually, this comes from this one with two definitions.
We'll use this device, known as a Faraday disc, to demonstrate how electrical current is generated in a conductor moving in a magnetic field. A large horseshoe magnet sits with its poles on either side of an aluminum disc. Two spring contacts touch the disc, one at the center, one near the edge, to provide electrical contact with the disc. As the disc is spun through the magnetic field, a current is generated, as seen on this galvanometer. Increasing the speed of the spin increases the amount of the current. Reversing the direction of the spin reverses the direction of the current. When this aluminum disc is turned, a bar magnet attached to a bearing begins to spin in the same direction. Reversing the direction of rotation makes the magnet reverse direction. If a rubber band is attached to the magnet, spinning the disc turns the magnet and stretches the rubber band. Spinning the disc at a higher speed makes the bar magnet turn farther. The amount the magnet turns therefore indicates the speed of the disc. A similar method is used in car speedometers to measure the speed of the turning wheels and thus the speed of the car. This demonstration uses an electromagnetic field to break a cola can into two pieces. An empty aluminum cola can is inserted into this three-turned coil. This 400 microfarad capacitor will be charged to 3,000 volts as read by this meter, and then will be discharged through the coil. Let's charge the capacitor. When the capacitor is discharged, it creates an electron current in the coil, which increases rapidly to a large value. As the current increases, it produces a magnetic field, which also increases rapidly with time. The rapidly increasing magnetic field induces an electric field circling the axis of the coil. This electric field produces a large electron current in the aluminum can. The electrons circulating around the can in the magnetic field experience a magnetic force directed primarily radially inward, but with a smaller component directed outward along the axis of the can. The capacitor is now fully charged, so we can turn off the charging power supply and discharge the capacitor through the coil. We will now repeat this action in slow motion.
A new look at electric potential. Induced electric fields are produced not by a static change, but by a changing magnetic field. Although electric field produces in either way exert forces on charged particles, there is an important difference between them. The simplest evidence of this difference is that the field lines of induced electric field form a closed loops. Field lines produced by static charges never do so, but must start on positive charges and end on negative charges. The voltage difference is minus E dot ds integration from I to final. Okay, if we do a loop, the final point is the equal initial point, so V final equal to 0. But induced electric field is different. The integration equal to minus d phi is not 0. Okay? So electric potential has meaning only for electric field that are produced by static charges. It has no meaning for electric field that are produced by induced. Example. In a figure, take R. This R, 8.5 centimeter, and dB dt 0.13 tests per second. The B changes increase uniformly. Question A. Find an expression for the magnitude of the induced current field at points within the magnetic field inside, at radius r from the center of the magnetic field. This is an evaluation expression for r equal to 5.2, and this big r is 5.8. This is inside the circle. Now we put the equation. E dot the integration, in this case, E by symmetry reason is the same magnitude, and the direction is always along the tangent. Okay, so this equation becomes E dot ds equal to E ds. E is constant, take it out. Integration ds is 2 pi r. And on the other side, minus d phi by dt, we see this is d phi. What is phi? Phi is b a. A is constant, take out dB dt. We have dB dt 0.13 test. So we get E equal to this r squared cancel out 1 equal to half pi cancel out L dB dt. You put a number, you get a number sign. Okay, remember, here we have to use the meter. They give in centimeters, so you have a time minus 3. Okay. Question B. Find an expression for the magnitude E of the induced electromotive force at points that are outside the magnetic field at radius r. Evaluate the expression for r 12.5 centimeter. Now, when r is larger than 1, d phi will be different. D phi is constant, or phi is constant. Okay, constant. Because outside, you don't have the magnetic field. Okay, so flux B is B, constant. That's the difference. We do this formula. This is the same on the left side. Okay, and the right side is minus d phi dt. This is a constant. This changes. Okay. So we put them right inside. We get E. Now, nothing cancel out. This is big R. This small r. 2 pi cancel out. So E equal to half. Okay, r squared over r dB dt. We put the number inside. Okay, we get the number. Okay. Inductors and inductance. An inductor can be used to produce a designed magnetic field. We should consider a long solenoid, more specifically a short length near the middle of the long solenoid as our basic type of inductor. If we establish a current I in the windings or turns of an inductor, a solenoid, the current produces a magnetic flux phi throughout the central region of the inductor. The inductance of the inductor is then L equals N phi over I, the definition, in which N is the numbers of the turns. L equals N phi over I. The windings of the inductor are said to be linked by the shared flux, and the product N phi is called the magnetic flux linkage. The inductance L is thus a measure of the flux linkage produced by the inductor per unit current. The metric system unit of inductance, this is a Henry, this is a flux, Tesla meter square, and this is ampere. As 1 Henry equal to 1 Tesla meter square over Henry. Throughout the rest of this chapter, we assume that all inductors, no matter what their geometric arrangement, have no magnetic materials such as iron in their vicinity. Such materials will distort the magnetic field of an inductor. Inductance of solenoid. N, the number of turns per unit length. This per unit length is per meter. L, the length of the solenoid. B, the magnetic field within the solenoid. We have learned in the last chapter, B equal to mu 0 N I. N is the turns per unit length. A, the cross-sectional area. L equals N phi over I. And N phi is N is the total number equal to NL. This is the turn per unit length. This is the length. And phi is BA. So we put this one here, we got L equal to NLBA over I. And B, we know that equal to mu 0 and I. Put this one B inside, I cancel out. So the L equals mu 0 N square LA. And we divide the L over the inductance per unit length equal to mu 0 N square over A. It's nothing to do with current. Thus, the inductance per unit length for a long solenoid near its center is L over mu 0 N square A. It depends only on geometric factors, nothing to do with current. If the solenoid is very much longer than its radius, then equation gives its inductance to a good approximation. This approximation neglects the spreading of the magnetic field lines near the end of the solenoid. Mu 0 can be expressed in the unit Henry per meter. Okay, this mu 0 can be Henry. Okay, so mu 0 equal to 4 pi times 10 to the minus 7 Tesla meter per ampere, equal to 4 pi times 10 to the minus 7 Henry over meter. Self-induction. Self-induction. We look at the circuit. You have resistance can be changed. Change the resistor so it can change current. Okay, this is a solenoid, a coil. Okay, so a current established in this circuit. An induced electromotive EL appears in any coil in which the current is changing. If we change R, change I, then we have induced electromotive force produced in this coil. This process is called self-induction, And the electromotive force that appears is called self-induced electromotive force. It obeys Faraday's law of induction, just as other induced electromotive force do. Faraday's law of induction plus inductance. This is Faraday's induction law, and this is inductance. We know inductance is defined by n phi over I. This is n phi. So we put n phi here equal to Li, and epsilon L equal to minus di dt. Okay. Thus, in any inductor, such as coil, solenoid, or toroid, a self-induced electromotive force appears whenever the current changes with time. The magnitude of the current has no influence on the magnitude of the induced electromotive force. Only the rate of change of the current counts. Well, look at this picture. If the current increases, and then we have self-inductance electromotive force equal minus LDC. We see if current here, we have induced against it change. So we have this electromotive, this is negative relative to this point. Okay. Otherwise, if the current reduces, then we have induced against the change. You have current here. So this is, in this case, this is positive, this is negative. Okay. The direction of a self-inductance electromotive force can be found from Lenz's law. The self-induced electromotive force acts to oppose the change that brings it about. The polarity of a self-induced electromotive force is then the potential after the coil comparing that before the coil. The potential after the current compared before the coil. In this case, it's negative. In this case, it's positive. Okay. Let me read again. The polarity of self-induced electromotive force is the potential after the coil comparing that before the coil. If you go along the direction of the current, this is the direction. In any case, it's direction of current.
This power supply puts out about 6 volts. When we touch the output leads together and separate them, no spark is seen. If we hook the leads to this solenoid coil with 2,000 turns of wire and disconnect one wire, a small spark is seen. When an iron core is inserted into the coil and the sequence is repeated, a larger spark is seen.
We'll use this inductor coil and a light bulb to show the effect of inductance on an alternating current. When the lamp and inductor are hooked in series to 110 volts AC, the lamp lights normally at first. If we increase the inductance of the coil by inserting an iron core, the lamp dims as the core is inserted into the coil. The current flowing through the circuit has decreased.
RL circuits. This is a circuit. You have RL. This is a circuit. Okay. We look at this RL circuit. We have learned RC circuit before, so now let's study it together. First, we switch to connect to electromotive force. And we assume the current in this direction. This is the current we assume. It doesn't matter which direction you assume. Okay. After you solve the differential equation, if the I is positive number, that means the direction. If I is negative number, that means the real I is that direction, okay? So we assume I is this direction. And under this assumption, the current charge capacity. So this plate is positive charge. This plate is negative charge. All right? Now we look this one. If we switch to A, we assume a current this ring. And this current goes down. This coil has self-inductance against the change. So this is positive, this is negative, E epsilon. Right? Now we look at this related equation. Okay. From here, epsilon positive minus IR. This is under this assumption, the negative. So we go this one as negative V. V is Q over C. This is a differential equation for this circuit. And we look at this one. This epsilon minus IR. And this one you see that self-induced electromotive force, this is positive, this is negative. So we have a minus L di dt. This is I is dq dt. So we rewrite this one. dq dt equal to Q over RC equals to epsilon over R. And this one is a di dt equal to plus I over L, I equal to epsilon over. They're very similar, only the difference is the sign, okay? And the initial condition. The initial condition is at the t equal to 0, there's no charge on this capacitor. So Q0 equal to 0. In this case, the I, so this one, okay, at the beginning, 0. No current, okay? So we solve this differential equation with this initial condition. Oh, also this differential equation with this condition, we get the answer. We know this before. The Q, the accumulated on this plate, equal to CE 1 minus E minus T over RC. What does this mean? Okay, T equal to 0, E0 is 1. 1 minus 1, 0. So when time T equal to 0, there's no charge of this one. We know that. And when T approach infinity, E minus T is 0, and Q equal to C epsilon. C is capacitor, epsilon is the voltage difference, as we know that. Now we look at this one. We saw this one similar, which is E equal to I equal to epsilon or R, 1 minus E minus T R over L. And we rewrite this. We put R in the denominator. So we can write it T over L over R. This is a T over RC. Okay. And then we see the current is dq dt. Get this one to the derivative with respect to time t. This is 0, it's minus, you get epsilon RC, you cancel C over R E minus 3. What does this mean? This means that when t equal to 0, this is a 1, and this I is epsilon over R, very large. And then when t approach infinity, this is 0, I reduce to 0. That's the situation for capacitor we have learned. Okay. At the beginning, R is very huge. Okay, Q is 0. And then with the charge, so the R getting smaller and smaller, finally I equal to 0. And the charge is the maximum, C epsilon. Look at this one. We know this one. The electric voltage induced, self-induced, equal to minus di dt. So epsilon is di dt, related to di dt. We will find that one, okay? Yeah. And this one equal to epsilon minus IR. We can calculate from this one, we get epsilon e to the minus t over L over R. Okay. What does this mean? What this means is when t equal to 0, E0 is 1. 1 minus 1, 0. I is 0. So at the beginning, I is not like this, such a wow, huge. No. I keeps 0 and gradually increase until t into infinity. This is 0. You get I equal to epsilon over r. Okay, and then e. The e is different. When t equal to 0, this is 1. So EL is equal to this very large. This is self-induced electromotive against the change. And I is 0. And then gradually I increase, E epsilon small, until this is 0. This is the maximum epsilon over R. And these two circuits will have this tau equal to RC. This tau equal to L of R. We call them time constant. What does mean, time constant? Time constant means when t equal to time constant, about 2/3, 67% has finished. Okay, when tau equal to 2, t equal to 2 tau, 95% process has finished. Okay. Now we look at, this is the data, VR, the voltage across the resistor. We look, VR is RII. So actually, this shape actually represents the current situation. Okay, and I, we know that equal to epsilon over R, 1 minus E equal to minus T over L over R. Okay, and this is also R cancel out, epsilon 1 minus E equal to minus C. We see the current between R, because I equal to 0. So at the beginning, T equal to 0, E0 is 1. 1 minus 1 is 0. V is 0. And when the t approaches infinity, e to the minus infinity is 0. So V finally equal to epsilon. Now, the time constant is L of R. Now we look at the voltage across the coil, inductor. We find at the beginning, it's very large because it's related with di dt. We have I, but di dt is, look at this curve, is the tangent of the slope. Okay, we look at this slope. Okay, it gets slow and a slow and a slow. So the VL gets slow and a slow and a slow. Okay, so VL is equal to epsilon e to the minus t over L over R. When t equal to 0, this is 1. VL is very large because self-inductance. Okay, and when t equal to infinity, VL equal to 0. And the time constant is tau L. Now we see that another S switch to, after it finished charge of C, and we switch S to this one. And we switch, in this way, we still assume I we can assume either direction, okay? Even though the real direction is the opposite. We just assume it and we do the calculation. We get the same thing, okay? If you assume this one, this is a positive charge, this is a negative charge, and we find this one, we switch B after it long time, okay? We switch this one, okay? Before we switch one, we have a current here. The I is epsilon over R. This voltage drop is 0, right? Now we switch to B. So what happened? First here, we have I, we assume I, also E is this one. So then we see this one is from here to here, minus Ri. I is dq dt. From here to here, minus V. V is Q over C, equal to 0. Okay? Equal to 0. And this one, you see, the current is minus IR. This one is, from here to here, is minus L di dt, minus IR equal to C. These two equations are very similar, So we know the answer. This answer, Q is C, T equal to 0, Q is C epsilon. It was already charged, okay? And this one, we know that, and before it switched one, we have a current. This current is epsilon of R. No drop here because compared to this one, its resistance is very small, almost zero. And then outside this Q is CE over E times T over RC. We did it before. And similar, we copy this one. Okay, I equal to epsilon R E minus T over L over R. This constant tau equal to RC. This time constant is L over R. Now, we prove L over R has a dimension of time, a second. L at unit is Henry, R is ohm. And we know that, okay, from this equation, we see that Henry ampere equal to volt second. Volt second equal to Henry ampere. And we see that, okay, 1 volt equal to ohm ampere. Then we see volt cancel out, ampere cancel out, ohm cancel out, Henry cancel out, we leave second. So L of R is a dimension second times dimension. Initially, an inductor acts to oppose changes in current through it. A long time later, it acts like an ordinary connecting wire. So R of this inductor, at the beginning, when current changes very fast, that means omega is infinity, changes very fast, the R is infinity. Infinity, I is zero. And for a long time of that, it looks like just a wire. RL approaches zero compared to other R. In this one's long time, we don't have a change omega to zero. Okay? Figure A shows a circuit that contains 3 identical resistors with resistance R 9.0 ohm, 2 identical inductors with inductance L 2.0 millihenry, and an ideal battery with electromotive force epsilon 18 volt. What is the current I? So the battery just after the switch is closed. Now, when just a switch closed, the change is a lot. In that case, as we mentioned before, this is infinity. That when it's open. So in this case, the I is epsilon over R. It's epsilon 18. This R is 2.08 here. Now, question B. What is the current I through the battery long after the switch has been closed? We notice that long after the switch has closed, everything is in equilibrium. This is just a wire, no resistance. So this becomes this one, this wire. So this becomes 3 identical resistance connect in parallel. So we replace R over 3, connect this one. So in this case, okay, R equivalent is R over 3, 3.0. Then I is epsilon over R equivalent, 6.8 ampere. Sample. A solenoid has an inductance of 53 millihenry and a resistance of 0.37 ohm. If it is connected to a battery, how long will the current take to reach half its final equilibrium value? First, we have to know what is the final equilibrium value. We know in LR circuit, the current IL equals epsilon over R times 1 minus E to the minus T over L over R. What the final equilibrium value? That means T approach infinity and E to the minus infinity is 0. So I infinity is epsilon over R. Now the question is, this I, what time equal to half final equilibrium value? This is the condition. And from this equation, we cancel is r, we get half equal to 1 minus 2c. So it's very easy to find the t. Okay, t equal to L log c quality. All right, and we put the number inside. L 53 millihenry. The unit should be Henry, so you have multiple 10 to the minus 3. Okay, and we get the time is about 0.990, about 0.1 second. Energy stored in a magnetic field. Well, look at this one. Epsilon equal to this one equal to IR plus L di dt. This is one is IR, this is L di dt, so they are equal. If we multiply by I on both sides, we get IR equal to I square R plus D half Li squared dt. We rewrite this one. You do the derivative, you get IL di dt. Now let's look at physics meaning. I epsilon is the rate, the power at which the seed of electromotive force delivers energy to the circuit. Okay? And I squared R is the rate at which energy appears as thermal energy in the resistor. So this one, d half Li squared dt is the change rate. What is it? So we see this one is the rate at which energy is stored in the magnetic field in this coil. Inside you have magnetic field, right? So this is total U in the coil is half Li squared. The L is the inductance of the inductor. I is the current passes through this inductor. This one represents the total energy stored by an inductor L carrying a current I. Note that similarity between the expression and the expression for the energy stored by a capacitor with capacitance C and the charge Q is UE equal to half CV squared. Now, L current of C, I current of V. Okay. Also, we can write this one half Q squared over C. Okay. Sample. A coin has an inductance 33 millihenry and a resistance 0.35 ohm. Question A. If a 12-volt electromotive force is applied across the coil, how much energy is stored in the magnetic field after the current has built up to its equilibrium value? Now, this is the answer. The current time is infinitive, so this is a final equilibrium current. Okay, and we know this final current equal to epsilon over R. This is 12 volt over 0.35 ohm, 34.8 meter. Okay, and we see how much energy is stored. This is put it inside. So this is half MC. We put it inside. Okay, this is 31 joule. Question B. After how many time constant will half this equilibrium energy be stored in the magnetic field? Now, we know that magnetic field store the energy. Half of it, okay, is how much time? We know this is the energy, okay? And now, question is, this is final, this is instant when and I want to find how much time will make this one equal to half it. Okay, half it. So make it equal, and what we found is the I. This I is one I infinity of square root. At I infinity, we know that is I over R. This is I at any time. This I final is epsilon over R square root. From this one, we cancel the epsilon over R, and we can find the T. I don't do it. Okay, it's simple mathematics. Okay? You're better than me. Okay, we find t about 1.2 L over r. This is a time constant. Okay, one comes up. So how many is 1.2? Now, let's see this picture. Okay, when we after long equilibrium, it turned to B. Okay? And when we shoot, you have I go this way. We still assume, okay? And we will have introduced electric force going up. This is negative, this is positive. And we know that at the beginning, the I0 is epsilon over R at the T, okay? Because long time is established. And we know I is epsilon R over E over minus over L over T. And the tau is L over R. Now, let me see how much thermal energy is released in this one. Because we know that when finally this I is 0, all the energy stored in the coil transfer to a heat energy of this R. Let me see, calculate. How much? So dW is I squared R over T. This I changes, okay? I is this one, okay? And the total energy is integration. W is this Q. And we put I into this one, okay? This one is epsilon of R of E to square. This is R dt. Integration from 0 to infinity. 0 to infinity. I don't know how long time. Actually, you don't need infinity, right? But we theoretically is infinity. And do the integration is easy one, okay? It's easy one. And we get equal to half L epsilon of R squared, okay? What is this? This is a T equal to 0, I0. So this is I0. What do we find? We find that the energy as dissipated at the thermal energy in resistance is equal to the total energy stored in the coil at the beginning. Okay? In other words, all the magnetic field energy is transferred to heat energy in the energy density of a magnetic field. Consider a length L near the middle of a long solenoid of a cross-section area A. The volume associated with this length is AL. The energy stored by the length L of the solenoid must lie entirely within this volume, because the magnetic field outside such a solenoid is essentially zero. Moreover, the stored energy must be uniformly distributed within the solenoid, because the magnetic field is uniform everywhere inside. The unit volume magnetic field, called the magnetic field density UB, equal to total energy stored in the solenoid divided by its volume. UVB equal to half I squared. We have proved before. And we know L over I is mu 0 n squared A, and we get that before too. And B in the center of the solenoid is mu 0 n I, where n is the turns number per unit length per meter. Now we do this one. This one, we put this one inside, half L squared, and that's it. And we find out, okay, L over I, this is L over L. Big L over small l equal to mu 0 n squared A. We put this one inside. And A cancel out. So we write it mu 0 squared n squared I squared over 2. This is mu 0. Y squared. Now we have another mu squared here. Okay. We wanted this one Why we want to now look at a b. Mu 0 n I is b. So this is b squared. So we get UB, the magnetic energy density, equal to b squared over 2 mu 0. This is formula you have to remember. Okay. This equation gives the density of the stored energy at any point where the magnetic field is b. Even though we derive it by considering a special case, the solenoid, equation holds for all magnetic fields, no matter how they are generated. The density of stored energy at any point where the magnetic field is B, where the UB equals half 1 over mu 0 and B squared, is compatible to UE equal to half epsilon E squared, very similar, which gives the energy density in a vacuum at any point in the electric field. Note that both UB and the UE are proportional to square of the appropriate field quantity B and E. And we will prove it, okay? They are equal, okay? Sample. A long coaxial cable consists of two thin walls, concentric conducting cylinder. Now, this is one, this is the two. They are concentric. Okay. The inner cylinder carries a steady current I. This is one I. The outer cylinder providing the return path for that current, the outside. Okay. The current set up a magnetic field between the two cylinders. Now this is between the two cylinders. Question A. Calculate the energy stored in the magnetic field for length L of the cable. Now, we want to find the energy stored in the cable. The length is L. Now, what we do? Now we do this one. First, we find the magnetic field. How do we find? We use the Ampere's law with the integration B dot ds equal to mu 0 r. Now we take this special case. This is location is r. The thickness is dr. Okay. Then the B at this point in this very tiny area is br. This side 2 pi r. Why? Because B is by symmetry reason everywhere is the same in magnitude, and direction, okay, is along the ds. So B ds, we integration the B taken out, okay, and ds is 2 pi r equal to mu I net. I net just the current inside, okay. So then the UB equal to B squared over 2 mu. We put this one inside. We get it. Mu 0 I squared, A pi squared R squared. It depends on the location R. Different R, you have different energy density. Okay? UB is a function of R. So when we do the total energy store, we have to use the integration. We take this small cylinder, the radius is r, okay, the length is L, and the thickness is dr. So this dV equal to 2 pi r L, the surface area of this cylinder, multiplied by dr. So this dV. And then we do the integration. Integration is from where to where? The question is total is from A to B, right? And cover whole the area. So it's from A to B. The leftover is very simple integration. I'm going to do it. So the answer is mu 0 I squared L 4 pi log B of A. We can do it different way. We're going to see UB equal to half L I squared. Okay, and we will find that we get the same answer of this one. Okay. Question B. What is the stored energy per unit length of the cable if A is 1.2 millimeter, B 3.5 millimeter, and I is 2.7 ampere? We just put the number inside. Very simple. Okay. Per unit length, we put the L over here. That's the energy stored per unit length is equal to mu 0 I squared 4 pi log B over 8. We'll put the number inside. We get the answer. So about 780 nanojoule per meter. Mutual induction. In the figure, we saw that if two coils are close together, a standing current I in one coil will set up a magnetic flux phi through the other coil, linking the other coil. If we change I with time, an electric motive force epsilon given by Faraday's law appears in the second coil. We call this process induction. We would better have called it mutual induction to suggest the mutual interaction of the two coils and to distinguish it from self-induction, in which only one coil is involved. Self-induction L is defined as N phi over I. In mutual inductance, we have a similar definition. Mu 21 equal to N2 phi 21 over I1. Mu 21 is mutual inductance 2 because caused by 1. N2 is the turns of coil 2. Phi 21 is the flux through coil 2 associated with current in coil 1. And I1 is the current coil in 1. This is mutual. That's mutual. Okay. This is the definition. Okay. A definition. And we know that M21 multiplied I1 equal to N2 phi. N21 is a constant, N1 is a constant. I1 can change, so phi 21 can change. We do the derivative with respect to time t on both sides. We have this kind of relationship. And we know that definition, the electromotive force induced in coil 2 by I1 is equal to minus N2 d phi 21 dt. And we look at this one equal to this one. So we get epsilon 2 equal to M21 minus di2 d1. This is electromotive induced by current change in coil 1. So this is di1 dt, and this is mutual inductance. This is similar to self-inductance, similar to inductance. Vice versa. So similar, if you change the current in coil 2, we can induce an electromotive force in coil 1. So we have epsilon 1 equal to minus M12 di2 dt. And M12 and M21 are same.
The high voltage for the spark plugs in a car is produced by a device called an induction coil. We'll use this induction coil to show the effect. Two coils are wrapped around a common iron core. The primary coil has a small number of turns made of relatively thick wire. The secondary coil has a much higher number of windings of thinner wire. This is a magnetic make and break switch. Current runs through the switch to the primary coil, and the magnetic field produced pulls the switch in towards the core, breaking the circuit. The magnetic field goes to 0, and the switch recloses, starting the cycle again. The pulsed current in the primary coil produces a high voltage pulse current in the secondary coil.
Sample. Figure shows two circular close-packed coil 1 and 2. The smaller radius R2 with N2 turns being coaxial with the larger R1 with N1 turns and in the same plane. Question A. Derive an expression for the mutual inductance M for this arrangement of these two coils, assuming that R1 is much larger than R2. Okay, now we know the definition is N2 phi F2 over I. That's the definition. Okay, now we find this one, then we can get it. Relate to I1. See the B1 inside. We learned this one. This is circle at the center, the B around this one. Okay, Z equal to 0 because just on that surface. Then you get R1 3, R1 1, you get R1, get mu Z, I1 N1 over C. You have N2, okay, N2. Okay, you got a B1. Suppose it is uniform. So N2 phi x2 equal to N2 equal to, this is B1 multiply area, okay? It's very small, so we thought it's uniform, okay? This area is pi R2 squared. We get this, okay? And we see the B, put in the B. The B you have I1, cancel out this I1. Okay, we put the B inside. Okay, you get this one for definition. Okay, then we get mutual. Question B: what is the value of M for N1 equals N2 equals 1200 terms? R2 equals 1.1 centimeter and R1 equals 15 centimeter, which is much larger than R2. So we put the formula. By definition, M, mutual inductance, N2 phi 2 I1. Okay, and we have calculated that one before, right? Yeah, we put in the raised sign, we get the answer. Okay, it's about 2.3 millihenry. Chapter 30, electromagnetic oscillations and alternating current. Welcome you make a comment and give suggestions so that this program can be more helpful. Acknowledgement. This video clip is a part of my lectures on college physics during 1990 to 2021, based on the adapted textbook Principles of Physics by Faraday, Resnick, and Walker, published by Wiley. The demo videos were bought from a company in USA by my university for teaching. They helped a lot. I'm sorry for not remembering its name to show my appreciation. It seems that they came from the University of California, Santa Barbara, where I got my PhD in physics. Thanks God.